All right, note card 19 provides extra practice using L'Hopital's rule. All right, so here's some steps to evaluating limits. Let's look at example 1. All right, I'm not too concerned about an indeterminate situation since I don't have a fraction that I'm evaluating with. Direct sub in, evaluate at 3. Performing the necessary computations. I'm going to add 54 and 5 and get 59 and subtract 9, so I get 50. No need for L'Hopital's rule. Try the direct sub in. If it works, wonderful, move on. All right, number 2. The limit of x cosine x as x approaches infinity. Try direct sub in. Everywhere you see x, replace it with pi over 6. Use the unit circle to find the cosine of pi over 6. Square root of 3 over 2. All right, rewrite as a single fraction. All right, number 3. Plug in 1. Immediately I can see I'm dividing by 0 because if x is 1, that's what results. So it's all about the numerator. If I don't get 0, then I'm done. I would say D and E. Okay, but when I do plug 1 in for every x, I do get indeterminate. If you want to factor, fine. Factor and cancel. Retry the 1. Otherwise, this is where L'Hopital's rule would work. Derivative of the numerator, 2x plus 5. Derivative of the denominator is just 1. Try the 1 again, and you're going to get 7. All right, let's look at 4. All right, try direct sub in. It's just saying a doesn't go to 0, any number but 0. As x goes to a, everywhere you see x, replace it with a, you're going to get 0 over 0. Indeterminate. Okay, you could either factor the denominator into a difference of 2 squares and continuing factoring until you can cancel the x minus a with x minus a in the denominator, or you can apply L'Hopital's rule. Just a little strange because of all the variables. All right, derivative of the numerator was just 1. Okay, derivative of the denominator, and again, remember a is a constant, so that derivative is 0, this derivative is 0. So we're just finding the derivatives of the variable part here, x. So that's what, 4x cubed? Everywhere you see x, replace it with a. So my answer is 1 over 4a cubed. We're up for number 5. We have a difference here on top, but notice that it also tells me that g of x is defined to be this cube equation. So you could actually just insert 3x cubed minus 5 here for g of x, and then evaluate g at 0 and insert that value here. Or you can just wait till the end, and I think I'll take that approach. Let me first of all plug in 0 wherever I see x. So I'm going to have g of 0 minus g of 0, which those are going to be the same values, so the difference is going to be 0. Plug in 0 to the denominator. So I do get indeterminate. So applying L'Hopital's rule, the derivative of the numerator would be g prime, which I'll come over here and find g prime in a minute. The derivative of this value, which is a constant, well, that's just going to be 0. Okay, move to the denominator. The derivative is 3x squared. All right, so it looks like I need to find g prime, so I'm going to come over here. Derivative is going to be 9x squared. All right, so I'll replace my numerator that I have here with the specific derivative. 9x squared over 3x squared. Well, I'm going to cancel the x squareds. Simplify 9 and 3, and I'm going to get 3, and the limit as x approaches 0 is still 3. Otherwise, you could have, plugged in what the g of x function was, subtracted whatever the value was when you plug 0 in, do some factoring, canceling, you'd still end up with 3. All right, for number 6, let's evaluate the limit at x equals 0. So that would be 0 plus the tangent of 0, which I know is 0, over the sine of 0, which is also 0. So this is indeterminate. Let's use L'Hopital's rule, because notice I can't factor anything. I mean, I could break this apart. I could say it's x over sine x, and then the limit of tangent over sine, and I could do some simplifying, and it would work out fine. Otherwise, I'm just going to use the new rule. Derivative of x is 1. Derivative of tangent is secant squared. So I'm going to get it ready because I know I'm going to plug in a value, and when I do that, I like to have the square on the outside. Derivative of sine is cosine. Plug in 0. Okay, well, I know the cosine of 0 is 1. That's easy enough. The numerator starts off with 1 plus. All right, secant of 0. I'm not going to work with secant. I'm only going to work with sine, cosine, and tangent. So secant is the reciprocal of cosine. So the cosine of 0 is 1, and we reciprocate it. So we have 2 over 1, or simply that answer is 2. All right, 7. Oh, it's been a long time since we've seen a problem like number 7. But we did have a shortcut rule at the time. We learned about these graphically from the calculator. If you were to insert 0, you're going to get sine of 5 times 0, or sine of 0, which is 0, and then you're going to have 2 times 0, which is 0. So this was indeterminate, and we saw that because of this structure right here. Graphically, we explored and found out that the answer is going to be the ratio of the coefficients on x. The answer was 5/2. So I didn't have to actually go through all this. I could have just simply said, oh, I remember this. That limit as x approaches 0, because I had indeterminate, gives 5/2. Well, let's say it's just one thing you don't remember. Here's something else you can do to also get 5/2. Because it's indeterminate, find the derivative of the top and the bottom. The bottom's easy. The numerator's derivative requires the chain rule. So derivative of sine is cosine, leave the 5x alone, multiply by the derivative of 5x, so I'll just put that in front here. Now try with 0. Cosine of 0, multiply first. Cosine of 0 is 1. 1 times 5 is 5. Answer is 5/2. All right, I had to handwrite number 8 in here. It's worth a look. I don't think you'll see anything this difficult, but I think it's still a good problem. I get to review some pre-calc identities. If you were to plug 0 in everywhere you see theta, you're definitely going to get 0 over 0. Indeterminate. If that's a 0. Oh. So the cosine of 0 is 1, so my numerator becomes 0. The sine of 0 is 0, and if you square it, it's still 0. Times 2 is still 0. All right, so I can try and find the derivative. It just seems like it'll be a little bit challenging, cumbersome, maybe tedious to find the derivative of sine squared. So, but what I do notice is that from pre-cal, there's a Pythagorean property that allows me to rewrite sine squared. So back to the drawing board. when we were doing our trigonometric identity unit, and this came up often, we rewrote sine squared as 1 minus cosine squared. The thinking was we can factor this difference of two squares and cancel it with one of the factors in the numerator, or the only factor in the numerator. These two factors will cancel. A little bit of cleanup. 1 on top, 2 times 1 plus cosine theta on the bottom. We didn't even have to use L'Hopital's rule. Our pre-cal took care of that for us. Plug in 0. Cosine of 0 is 1. Added to another 1. 1 plus 1, 2. 2 times 2 is 4, so the answer is a fourth. So we didn't even have to use L'Hopital's rule. All right, and as a final limit on this page, let's look at number 9. All right, we're going to plug in 0. So 0 times the secant of 0. Well, secant of 0, I think we saw earlier, was the cosine of 0 reciprocated. So cosine of 0 is 1. Reciprocate 1, you still get 1, but 1 times 0 is still 0. So not all of these problems involve L'Hopital's rule, but it was a good review of limits and when you'd probably want to use that shortcut.